And it's just so hard to find. Like, where? Oh, I see you now. If you ever do find the true value, consider yourself lucky. I guess you could say that analytical chemistry is the search for truth, looking for the true answer, that is. And one of the ways that helps you to do that is to know a little bit about statistics. So first we're going to talk a little bit about error. And I do have to confess, with all of these videos that I'm producing for you, I'm bound to make a mistake or two, or 10. So if you ever find something that seems a little bit questionable, just let me know. I'll try to fix it as best as I can. And we'll also go through some of the basic statistics. I think you'll know most of these things, although maybe the difference between absolute and relative standard deviation is something new. Okay, so we can't get into the lab, but let's learn the most fundamental skill for an analytical chemist right here. How to read that number.
Do I detect a note of sarcasm?
Are you kidding me? This baby is off the charts. Why?
Now, you're probably already aware that you can read this number by looking at all the divisions. So 21, 22, I count 10 tick marks. So 21.3, right? That's the correct answer. Now, if you really take a close look, you could probably divide those divisions a little bit further. Can you divide it in half? Can you divide it in 10? That's really up to you. So I'm going to say that you can actually put another decimal place on that number. And you're probably wondering, well, how do I know if I'm supposed to read the bottom of that line or the top? Like when we're really getting down to it, that's probably going to matter? Actually, it doesn't, as long as you're consistent. So if you decide the bottom of the line is where I'm going to take the reading, then you'll be good with that. But you should be able to read a burette with an extra decimal place by kind of cutting the invisible divisions between. One thing you should never do is read from the top. So if you're saying that that number is 22.7 because 22 and you're counting up to 7, that's definitely wrong. Now here's something that I've personally never seen in the lab. Somebody who fills up a volumetric flask and goes way over the mark. In fact, it's kind of the opposite, where you spend a lot of time drop by drop to make sure that you don't go a little bit higher than the meniscus. If you did this, then obviously you've made a mistake. However, it's what you don't see that might really matter. So in this case here, we have some salt, and you can tell that the salt is quite damp. In fact, it's like soaking wet. So if you're weighing this salt, then you're going to be weighing a little bit of salt and a little bit of water. The true mass of the compound that you're supposed to be weighing is less than what your reading is going to be. So that's going to cause a mistake. Either way, these two errors are what we would call a real screw-up, a blunder, the types of things that you would never want to do, as long as you have the basic sense to be able to avoid these things. So let's talk about some different errors, the type of errors that are either very hard to avoid or downright impossible. And the first one is the impossible type. So we call these random or indeterminate errors. Let's say, for example, you're working with an analytical balance, and this one happens to read to 4 decimal places to the 10th of a milligram. That's pretty impressive. But even though you're using this balance right, this balance happens to be calibrated correctly, it's still got error in it. In other words, the true mass has numbers after the fact. Even this 2 might be off by, maybe it's a 3, maybe it's a 1. So the true mass of our compound is better than what this balance can read. Likewise, when we're dealing with filling a pipette, you can do your very best to fill it exactly to the line. But even when you do that, and if you use this pipette over and over again, you're going to find that the volume that you deliver is going to be a little bit off each time. Maybe not even noticeable, but there will be a little bit of error within that. So this is what we would call random error. So the second type of error is a lot more difficult to spot. So let's take this example here of a bag of chips. Now, the manufacturer would tell us that the bag of chips is supposed to be 40 grams worth of chips. It doesn't matter whether it's filled with air or not. It should be within a tolerance and say 40 grams. That's what you're paying for. In fact, the manufacturer would have a tolerance on that. So their machine, their lineup is going to say that it's always within plus or minus 2 grams. So they're trying to sell you as close to 40 grams, but be within that tolerance. If you happened to open up 100 bags of chips and weigh them all out, and they always weigh low, 34 grams, there's a bias. There's an error that should not be there. Now in the lab, errors such as these creep up in ways that are much more difficult to find. So we'll show that a little bit later on in this video. But right now I want to talk to you about tolerance. So here we have a 100 ml volumetric flask. When you have this flask, it's going to say plus or minus 0.01. That refers to the tolerance. It says if you use this flask, it should give you a reading within that range. Now, where does that number come from? Does it come from the fact that you're going to be using it and be a little bit high and a little bit low? Well, actually, it's something different. This happens even before you started to use this particular flask. So let's say that the line here represents exactly 100 mils. At least that's what the manufacturer hoped it would. But what if the line was supposed to be here? Maybe this is 100 mils, or maybe it was supposed to be a little bit higher. So that's what the tolerance actually comes down to. Every one of these flasks that's made, hundreds, thousands of them, is not going to be exactly 100 mils. By the time it arrives on your doorstep or in the lab, you're already going to be using a flask that can be no better than the tolerance that it supplies you. So your textbook shows you pictures like this. And actually what we're talking about here is the combination of accuracy and precision and how they're influenced by error. So in this measurement here, we're going to assume that this line represents the true value. The thing is, we don't really know what that is, but let's just say for now that we know it's here. And all of these pinpoints represents our measurement of that true value. We're doing the measurement over and over again. And you can see that in this case, the measurements are very close to each other. So we're talking about precision. And if you look at the average of those lines, they're lying right up with the true value. So that means that these measurements are accurate as well. Looking at it on the bullseye, you can kind of relate which one of these things go together. So you're picking that one right there, right? So you're always hitting the bullseye consistently, high accuracy and high precision. Now, what about this case here? So you can see the true values at the same spot, but now our replicates are spreading a little bit higher. However, the average of these replicates actually still tends to the middle. It's kind of weird that like on our bullseye, we never hit the bullseye, but if you take the average of all of them, they're hitting the middle. So having poor precision can be okay as long as you do enough measurements and pool the data. Replicates are always a helpful thing when it comes to making a measurement. Now let's look at this scenario here. We're taking a bunch of replicate measurements, and again, they're all very close to each other. So that bodes well. It makes it seem like we're probably hitting the true mark, but we don't know what the true value is. Maybe this is where the true value is. Our samples are just reading high every single time. That's where that bias is coming in, the indeterminate error, the error that's very difficult to spot. And the reason why it's hard to spot is because we don't even know what the true value is. All we can really tell is the precision in our measurements. Accuracy and precision are closely connected, but they're not synonymous. All we can really do is try to eliminate error as best as we can. So the bias that may exist, for example, our instrumentation may be off calibration, maybe you have a poor choice of glassware. We're going to try to do our best to make sure that that's as close to the real values as they should be. There are ways to check this, but I won't get into them right now. Instead, what I want to talk about is replicates. So if we take a bunch of replicates of the same sample, so measure it again and again and again, the fact that we're taking multiple readings allows us to work with these numbers to come up with a better answer. Once we have our replicates, there's a couple of simple things you can do with the data. The first one I'm sure you're familiar with. We can calculate the mean. And the mean is simply just to take all the numbers, add them together, and divide by the total number of replicates. Let's just look at our data over here. If we're to calculate the mean, you can see that it's 0.5216. In fact, my calculator would say 0.6666666. But the fact that we're reading things to three significant figures, I'm going to report the answer as 0.522. Now, the next thing we can work with is something called a standard deviation, which I'm sure you're also familiar with. So here's the formula for standard deviation. It's kind of a long one, especially when you have a lot of numbers. But we can calculate a standard deviation, which is really just measuring the spread in our data. Without a doubt, the easiest way for you to do that is actually with Excel or a similar spreadsheet program. Remember that all your tests are going to be done at home, and I'm going to welcome you to use Excel. Personally, I prefer to use a spreadsheet calculator to my traditional calculator, so you're welcome to use that as well. So if you haven't used Excel to calculate a standard deviation before, it's really simple. This is the formula that you need, STDEV, and then you call up the array of the numbers that you have. And that gives you this value over here. Now, when you're reporting standard deviations, we can refer to them in two different ways, either an absolute or a relative standard deviation. So let's talk about the absolute one first. Here's a new example of data from Excel. In this case, all of the replicates refer to a mass. So if I'm going to calculate the average, then you'll come up with a number, and the units of that will obviously be the same as the units of our replicates. So the average is in grams. We can calculate the standard deviation in a similar way, and we're going to get a number. The units on the standard deviation will also be in grams. So this is an absolute standard deviation. So how would I write this number down? Well, the first value refers to our average plus or minus a standard deviation, and both of them carry the units of grams. Let me just rearrange the data. So you can see here the decimal places that we have in our numbers. The uncertainty in my value, in the average, comes out in the third decimal place. So what this is really saying is that 0, we don't really know what it is. In other words, the 1, maybe it's a 2 or 5, it could be higher, it could be lower as well. So what's the point reporting these values when we already are not sure what the value is at this point? So I'm actually going to delete that last number and decide how many digits to place based on the precision that we're reporting. Likewise, the standard deviation, if I'm unsure about the 4, well, I'm not sure about the 9 either. So the rule for reporting a standard deviation is just to put 1 digit right there. So how many digits you put in here depends on how far down the line you get with your standard deviation. This is sort of like sig figs, but it's a slightly different way of dealing with the numbers. So absolute standard deviation carries the same units as our average. The relative standard deviation is just a different way of reporting it, and we're going to get rid of the units entirely. You could think of it as a fraction or almost like a percent. So relative standard deviation comes about by dividing the standard deviation by the average. Okay, and when you do that, you see that the units cancel out. So the number that we have is just a ratio, the standard deviation divided by the average. If you'd prefer to report this as a percentage, you can just multiply it by 100 and you get 2.5%. In fact, if the number is really small, like 0.00000, you're allowed to multiply by 1,000 or 1,000,000, and now you'd be reporting a relative standard deviation in parts per thousand or parts per million. So these are some of the topics that we'll talk about a little bit later on as we move throughout this course. That's it for today.